Hi everybody, the purpose of this video is to go over section 3 of chapter 9 where we are going to talk about rational exponents. In this video we are going to review rational notation, talk about principal roots, review our rule for exponents and actually extrapolate on a couple of them, and then we're going to use those rules to, yes, you guessed it, simplify rational exponents. Okay, so this is our discussion on rational notation. First, notice that for any positive integer n and for any real number a, we can actually write the nth root of a using this radical sign. However, keep in mind that this is actually equal to a raised to the 1 over nth power. Now, the radical expression is, well, guess what? It's called a radical expression. The positive value n on the upper left-hand side of that radical expression is called the index, and the value a inside the radical expression is called the radicand. And now we want to talk a little bit about the conditions that we will impose on n for certain various values of a. And the first thing we want to mention is that for positive values of a, n can be any index out of once. Okay? However, for negative values of a, we can only accept odd values of the index. Why? Because if a is negative and n is even, then it turns out that the nth root of a, or a raised to the 1 over nth power, is not a real number. As an example, if you wanted to take the 16th root of -4, which would be a lot of fun to do, it will turn out that this number is not a real number, is actually an imaginary number, and dealing with such numbers is beyond the scope of this particular course. Okay, now the first thing that we are going to deal with is evaluating the principal nth roots. That actually should say principal nth roots and not prince nth roots. I was not trying to imply loyalty here. And how do we deal with such things? Well, I'm glad you asked, because I'm going to show you. Okay, let's take a look at our first example here. Now, notice that we have 49 over 81 to the 1/2 power. And if you recall from our last lesson, 49 can be written as 7 squared, because 49 is indeed a perfect square. And 81 can be written as 9 squared, because 81 is indeed a perfect square. As a consequence, when we raise that to the 1/2 power, we can use the power of we can use our power rule with exponents to write the numerator as 7 to the 1/2 times 2 power, and we can do the exact same thing in the denominator. We can write that as 9 to the 2 times 1/2 power, and that will be equals to 7 divided by 9, which would be the answer to this particular problem. Okay, now what about this one? Well, it turns out that 625 is actually equal to 5 raised to the 4th power. That's why we call this, and that's why we would call 625 a principal root. And if 81 is equal to 9 squared, and 9 is equal to 3 squared, then one could argue that 81 is equal to 3 to the 4th power. And we are going to raise all these to the 1/4 power, which is basically another way of saying we're going to take the 4th root. In that case, in the numerator, we will have 5 raised to the 4 times 1/4 power. And that should be a 4 and a 2, my apologies. And in the denominator, we will have 3 raised to the 4 times 1/4 power. Simplifying the exponents, we will once again have 5 divided by 3, which was our desired answer. Now take a look at the last term. This one here is -256 raised to the 1/4 power. Now, in radical notation, we could write that as the 4th root of -256. So we have an even index and a negative radicand, or an even index in our radical expression and a negative radicand. As a consequence, this has no real valued solution. Okay, now that we've dealt with that, now we can talk about review our rules for exponents. And the first two you should remember. The exponent 1 basically means that a raised to the 8th power is just simply 1. The exponent 0 rule, any number raised to the 0th power will always be 1. And from chapter 3, we have the product rule, which basically tells us that the same base raised to two different values, and we're taking the product of it, then we will basically, that will be equal to the base times the sum of the exponents. Similarly, for the quotient rule, we have if we have a raised to the nth power divided by a raised to the mth power, that will be equal to the a raised to the difference of the exponents. And then finally, for negative exponents, well, not finally, but at least finally for this slide, for negative exponents, if you have a raised to the negative nth power, that can be rewritten as 1 over a to the positive nth with that in the denominator. And if you have 1 over a to the negative nth, where this is in the denominator, then that will be equal to just simply a to the nth. The other rule that we talked about in chapter 3 was the power rule, which basically tells us that if a to the nth is raised to the mth power, and that being shown with the m being outside the grouping symbols, then that will be equal to a to the m times nth power. And an application of the power rule is with the power of a product, and there if we have a raised to some exponent and b raised to another exponent, and that group is raised to the mth power, then we will have a raised to the m times nth power and b raised to the k times mth power. And of course, we also have a similar rule for the quotient. And we have the negative exponents rule again, because, well, I actually forgot to delete that when I copied this slide over. And now we are ready to talk about dealing with radical exponents, at least in the general form. And take a look at what we have here. This is the power notation, and in power notation, a number raised to a rational exponent will be a raised to the m over nth power, and that's what it'll look like. Again, this is a rational exponent because we are assuming that m and n are integers, and therefore this exponent actually is a rational number. The radical notation looks just like this. It is basically either it is the nth root of a raised to the mth power, or it is the nth root of a, all that raised to the mth power. We tend to look at it like this. However, when we evaluate numbers or expressions that are raised to a rational exponent, I tend to do it in power form. Because it's easier to work with in the math. And also notice that there are two ways to do this. If I want to compute a raised to the m over nth power, I have two choices. I can first raise a to the mth power and then take the nth root of that, or I can take the nth root of a and then raise that to the mth power. You'll find that in many occasions the latter provides us a better way of finding a solution. And let's show that with a couple of examples. Here we have 125 over 256 raised to the 2/3 power. Now if I wanted to, I could either, I'm going to do this up here, I could compute 125 over 216 squared, and then I can take the third root of that. Okay, the only problem is I really don't know what 125 squared is, and I also don't know what 216 squared is. I could actually go ahead and compute that, but off the top of my head, I don't know exactly what that is. Okay, but what I can do instead of trying to squaring this first is I can take the third root of 125 over 256. That would give me 125 divided by 216, I keep on saying the wrong number there, the third root of that, and then I'm going to square it. Now does that work? Does that work better? Well, for me it does, because I know what the cubed root of 125 is. The cubed root of 125 is 5. 5 times 5 is 25, times 5 is 125. I also know what the cubed root of 216 is. The cubed root of 216 is, well, 6. 6 times 6 is 36, times 6 again is 216. Okay, so I've taken care of that, and now all I have to do is now square. And 5 squared is 25. 6 squared is 36. And there we go. That's how we deal with this particular problem. Okay, the next one, I'm going to change color since I'm sort of space constrained here. The next one is negative 343 over 64 raised to the negative 2/3 power. Now notice that I have an odd denominator here, which basically means I have an odd index, so there's no problem doing this particular calculation. However, I do have a negative exponent, and I can turn that into a positive exponent by taking the reciprocal of the argument, and that would give me negative 64 over 343 raised to the 2/3 power, now the positive 2/3 power. Okay, once again, I can find this to be an easier problem for me if I take the cubed root first and then square the result. So I'm going to look for the cubed root of negative 64 over 343, and then I'm going to square that. Well, the cubed root of negative 64 is negative 4. Negative 4 times negative 4 is 16, times negative 4 is negative 64. The cubed root of 343 is 7. And we know that because we've actually dealt with this in the last few in the last few sections. So once I figured all that out, I can now go ahead and square, and that will give me negative 4 squared, which is 16, divided by 7 squared, which is 49, which would be the answer that we are looking for. Okay, and this brings us to part C. Now, when dealing with problems like these that actually have variables in it, I prefer to group the coefficients together and then the variables together. And if I did, I will have 3 times 3 times x to the 1/2 power times x to the 1/3 power times, you guessed it, x to the 1/3 power. Well, 3 times 3 is 9. And then for the rest of this, I can use the product rule. And that would be x to the 1/2 plus 1/3 plus 1/3 power, and then that would be equal to 9 times x to the 1/2 plus 2/3 power. And so to complete this problem, I need to evaluate or add this fraction. And to do that, I need more space. So I want to compute 1/2 plus 2/3. Now to do this, I need to find a common denominator, and I would prefer that that common denominator be the least common multiple of 2 and 3, which of course would be 6. Okay, well I can change my 1/2 into a common denominator into a fraction with the denominator of 6 by multiplying it by 3 over 3. And if I do, I will have 3 times 2, which is 6, and 3 times 1, which is 3. I can turn 2/3 into a fraction with the denominator of 6 by multiplying multiplying that fraction by 2 over 2. And if I do, I will have 2 times 2, which is equal to 4. And of course 2 times 3 in the denominator, which will be equal to 6. And now I can add these two, and that's just a simple matter of adding the numerators. 3 plus 4 is 7. The denominator comes along for the right, and I have 7, 6. As a consequence, for C, we will have the answer of, let me just bring this up here, of 9 times x to the 7/6 power. And that will be our answer. Okay, now for our last one, we will use the quotient rule. And we can rewrite that one as x, or using the quotient rule, we can re-express this as x to the 3/4 power minus the 5/6 power. So solving this problem reduces to computing 3/4 minus 5/6. Okay, well, once again, we need to find a common denominator. We would prefer that common denominator be the least common multiple of 4 and 6, and that would be 12. 3 times 4 is 12, and 2 times 6 is 12. As a consequence, we want to multiply 3/4 by 3 over 3. And if we do, we will have 3 times 4, which is 12 for the denominator, and 3 times 3, which is 9 for the numerator. For 5, 6, we want to multiply that by 2 over 2. That will give us 2 times 6, or 12 in the denominator for the second term. And we will have 2 times 5, which is equal to 10 as the numerator in the first time. And now that we've done that, we can actually combine the numerators. That will give us -1, and the denominator comes along for the ride. So it turns out that x to the 3/4 divided by x to the 5/6 is going to be equal to x raised to the -1/12 power. And as you know, we don't like negative exponents. So to get rid of the negative exponents, we are going to use our negative exponent property and rewrite this as 1 over x to the 1/12. And that would be our answer for this particular problem. And for our last example, we are going to deal with the problem of simplifying expressions with radical notations. And the way that we're going to do this is by converting these radical expressions into, or these expressions that are in radical notation into expressions that are in power notation. Now note here that the cubed root of b to the 5th because actually can be written in power notation as b to the 5/3. And then the cubed root of b to the 7th can be written as b to the 7/3. As a consequence, we can write this product as a product of b to the 5/3 times b to the 7/3. And then we can use the power or the product rule. And using the product rule, we know that this will be equal to b to the 5/3 plus 7/3. And that means, and since we have common exponent or common denominators already, we can just go ahead and sum the numerators and bring the denominator along for a ride. And that will give us b to the 12 over 3. Notice that 12 and 3 both have common factors. Yeah, it's 3. So we can divide 12 by 3, and that will give us b to the 4th, which is our desired answer. For our second problem, we have the square root of x, which we can write as x to the 1/2, divided by the 4th root of x cubed. That's a little typo there. So the first thing we want to do is express both terms in power notation. So for x, the square root of x, we can write that as x to the 1/2 power. And then for the 4th root of x cubed, we can write that as x to the 3/4 power. Now using our quotient rule, we can rewrite this as x to the 1/2 minus 3/4 power. And now we just need to figure out what 1/2 minus 3/4 is. Well, once again, we need to write this as a common denominator. And the least common multiple of 2 and 4 would be, well, 4. Because 2 times 2 is 4, and 4 times 1 is 4. Okay, and all we need to do here is multiply the 1/2 by 2 over 2. And if we do, we will have 2 times 2, which is 4 in the denominator. 2 times 1 is 2 in the numerator. And we don't need to do anything to the second fraction since it already has a denominator of 4. So we'll just bring the 3 along. And now we can do our subtraction, and that should give us -1/4. So this is going to be equal to x to the -1/4 power. However, we have a negative exponent. That's not allowed, so we are going to rewrite that as 1 over x to the 1/4. And that is all I have for the lecture portion of this video. Just stay tuned, and we will bring up Hawks in practice mode. Okay, this is our first problem, and we need to compute 36 over 25 to the 1/2 power. Kind of like our very first example. 36 over 25 to the 1/2 power. We notice that 36 is a perfect square and can be written as 6 squared. We know that 25 is a perfect square. It can be written as 5 squared. All that raised to the 1/2 power. And then using the power rule, we realize that this is equal to 6 divided by 5. And there we go. This one would be worth doing as well. Here we have 25 over 27 to the 3/2 power. Now, once again, like I mentioned before, most of our problems are probably easiest to solve by looking at the root first. So let's write this as 125 divided by 27, where we look at the cubed root first, and then we will square it. Okay, well, the cubed root of 125 is a perfect cube. The cubed root of 125 is 5. 27 is also a perfect cube, and the cubed root of 27 is 3. And if we square that, we will have 5 squared, which is 25, and 3 squared, which is 9. And there you go. Now here we have negative 1 over 64 raised to the negative 2/3 power. Now we do have a negative number, but our index, which is basically the denominator of the rational power, is odd. So we can actually go ahead and compute this. First, we want to deal with the negative exponent, and we can deal with that by taking the reciprocal of 164, and that will negative 1 over 64, and that will give us negative 64 to the positive 2/3 power. And then we want to compute this the way we've done the other ones. We actually want to compute negative 64 to the 1/3 power, the cubed root of negative 64, and then we want to square whatever that result will be. Well, it turns out that negative 64 is indeed a perfect cube. 4 times 4 times negative 4 times negative 4 times negative 4 is equal to negative 64. So the cubed root of negative 64 is nothing more than negative 4. And now if we square that, we will get positive 16. And there we go. Okay, so let's see what other kind of fun things we have going on here. Okay, well, this is quick, so we'll just go ahead and do that. This is the square root of x squared times the square root of x squared. Well, you'll never guess what the square root of x squared is. You're right, it's x. Okay, so we have x for this times x for that, and that gives us x squared. And there we go. Okay, let's do this one, and this might be our last one. Here we have 5x times 2x to the 2/3 power times x to the negative 4 power. Now you might be tempted to throw that in the denominator, but you don't want to do that yet. We might want to do that at the end of this computation. But for now, what we want to do is we want to combine all the coefficients and then combine the variables with the variables with the same symbols. So we're going to have 5 times 2, which is 10, and then we're going to have x times x to the 2/3 times x to the negative 4th. Now, using the product rule, we can write that as the sum of the exponents. That's going to be 10 times x raised to the 1 plus 2/3 minus 4 power. And this reduces to computing 1 plus 2/3 minus 4. So we need a common denominator, and that denominator should be the least common multiple of 1, which is the implied denominator for 1 minus 4, and 3. So that would be a common denominator of 3. So we have 1 plus 2/3 minus 4, and that's going to be equal to something divided by 3 plus 2/3, because we're not going to mess with that, plus something else minus something else divided by 3. Okay, we can multiply the 1 by 3 over 3 to get our common denominator. Then we'll have 3 times 1, which is 3, and 3 times 1, which is 3. Furthermore, we can multiply our 4 by 3 over 3. That's because 3 times the implied 1 is 3, and 3 times 4 is 12. And now we can add our fractions. We can add the numerators and then let the denominator come along for a ride. And we will have 3 plus 2, which is 5, minus 12, which is negative 7, divided by 3. And therefore, our answer is going to be 10 times x to the negative 7/3 power. Okay, now unfortunately we can't read it like that because we have a negative exponent, but we can rewrite this as 10 divided by x to the 7/3. And there we go. Hopefully this is right. No promises. No, I made a mistake. What kind of a mistake did I make? Well, apparently I made a mistake, and I know what my mistake was. I forgot to get rid of my minus sign. So let's get rid of that, and let's try it again. There we go. Much better. And let's go ahead and do this last problem. This is problem 10, and this is x to the 1/2 raised to the 1/4 power. And this is an application of the power law. What we want to do is we want to write this as, since this is the power law, this is going to be equal to x raised to the 1/2 times 1/4 power, and multiplying the exponents, multiplying the fractions together, we will have x to the 1/8 power, and that should be our answer. So we're going to do x, then the caret above the 6 for the power, then the slash for the fraction, and then we will have a 1/8, and that should be that. Okay, and that is all I have for this lesson. If you have any questions, please feel free to contact me. And this is Bob Boyle, signing off.